Alrighty, let's look at some problems on moments. So we've got two apples placed on a balance, and we can see that they are equal distances from the pivot, and it says the balance stays level. What does this show about the mass and the weight of the apples? So if it's balanced, the moments of their weight force must be equal, and if they're the same perpendicular distance from the pivot, that must mean the weight forces are equal. And as they're on the same planet, that must mean their mass are equal. So that gives us option D. Okay, so then a student tries to balance a 10-kilogram bag of rice on a pivoted beam using a 5-kilogram bag of rice. What should be done to balance the bags? Well, at the moment of the weight force of the 10 kilogram is bigger than that of the 5 kilogram, which is why it's tipped up like this. So we either need to reduce the moment of the weight force of the 10 kilogram bag or increase the moment of the weight force of the 5 kilogram bag. So if we add some rice to the 10 kilogram, that's going to increase the anti-clockwise moment, so that's not going to help. If we empty some rice out of the 5 kilogram bag, that's not going to help either. That would decrease the moment clockwise, so that's the opposite of what we want. Move the pivot away from the 10 kilogram bag. Nope, that would increase the moment of the weight force of the 10 kilogram bag. Move the pivot towards the 10 kilogram bag. Yes, that would help. That would decrease the moment of the weight force of the 10 kilogram bag and increase it for the 5 kilogram bag, so that's perfect. Okay, so what is meant by the term moment of a force? So we often describe the moment as a turning effect, and it's the effect found by multiplying the force by the perpendicular distance from the force to the pivot. So a sawn off branch of a tree is laid across a log. The branch balances when point A is in contact with the log. How does the moment of the part of the branch to the left of A compare with the moment of the part to the right? Well, if it's balanced, the moments must be equal. The clockwise moment must equal the anti-clockwise moment. Otherwise, it's not going to be in equilibrium like it says it is. Mark clearly using letter X the center of mass of the whole branch. Well, if it's balanced, the center of mass must be at A, so the weight force acts straight through the pivot and it doesn't have an overall moment. A child of mass 40 kilograms sits at one end of a seesaw. The pivot is at the center of the seesaw. There are 4 sacks of sand, each with different mass as shown. So the key is the fact it says the center of the seesaw. So we essentially are going to need the same mass as the child in order to balance it. So we need 40 kilograms, so we're going to need the 30 kilograms and the 10, so we're going to need 2 sacks. Okay, so a uniform beam AB of weight W is balanced at its midpoint on a pivot. The two weights W1 and W2 are then hung equal distances from the midpoint. When this is done, end B moves down. Which is the heavier weight? Well, it must be W1, because its moment must be greater than the moment of W2 to make B go down. Which way would W1 have to be moved so that the beam is again balanced? Well, we would have to move it to the left to decrease its perpendicular distance, to decrease its moment until its moment is equal to the moment of W2. So we've now got rid of W2. This means only forces acting are the weight of the beam and also W1. W is much greater than W1. Mark a possible position for the pivot to be placed so the beam is balanced. So we need to have them on opposite sides of the pivot so that their moments can act against each other. So it's got to be between the two forces, and it needs to be closer to W so that W's perpendicular distance is smaller to counteract the fact that W is much bigger than W1. Okay, so this diagram shows a simple beam balance made from a pivot and a meter ruler. We want to find the mass of the bag of sand. So you'll notice that both of the objects are 48 centimeters from the pivot. So if this is in equilibrium, they must have equal weight forces and therefore equal masses. So we know it's got to be 0.75 kilograms for the two moments to cancel each other out. And then if we know the mass, we can use W equals mg to calculate the weight force, essentially multiplied by 10. Final part, explain in terms of the moments of forces why the beam balances. Well, the anti-clockwise moment of the weight force of the sand, so they can see that's acting to rotate it anti-clockwise, is equal to the clockwise moment of the 0.75 kilogram mass's weight force. It's those two moments that cancel each other out, and that leaves it being in equilibrium. And just to finish off with this one, it's also in equilibrium in terms of resultant force, because the upward force from the pivot is equal to the two downwards weight forces, giving us the complete condition of equilibrium. But this question asked us only about in terms of moments, so I didn't put that part in there. Okay, so the final question we're going to look at is a classic moments type question, which is a ladder problem. So let's start off. So complete the following statement. An object is in equilibrium when both the blank and the blank on an object are 0. So the two things we need are the resultant force and the resultant moment on the object should be 0 for it to be in equilibrium. Okay, so we've got a ladder. The end A is at rest against a vertical wall, and we can see there's a normal force from the wall, F, pushing outwards. And we also got it at rest on the ground, and there would be a normal force upwards from the ground. There might even be some friction involved here as well. Okay, so the diagram shows the two forces on the ladder. So the only force at A is F, so there's no friction on the wall. And that acts normally, so at right angles. The weight of the ladder is 240. Calculate the moment of the weight about point B. So to get a moment, we need the force and the perpendicular distance to point B, which is on the diagram 1.2, and that would be 290 Newton meters to 2SF. Now it asks us to write an expression in terms of F for the moment of F about point B. Well, F acts horizontally, so we need a vertical distance, and the distance, and if you can see in the diagram, is 3.2. So it's going to be 3.2 F. So we know these two moments must be equal to each other as they are the only force. So we can say 3.2 F must be equal to 2.88. And therefore we can solve what F is. It's 90 newtons pushing across to the right. So actually this tells us there must be a frictional force at B acting to the left to counteract this. Explain why there must be an upward force acting on the ladder at B. Well, if you think about the scenario at the moment, in the vertical direction, we've only got the weight force of the object, which is currently unopposed. So if there's not an upward force at B, there would be a resultant force downwards and the ladder would accelerate into the floor, but it's not, so there must be an upward force at B. So a body is in equilibrium and is acted on by two vertical downward forces in a way that there is no net moment about pivot. A student is asked to show this experimentally. The student is provided a suitable pivot, a meter ruler with a hole drilled in the center, two sets of masses, and strong cotton. How are we going to set this up? Well, we're going to have a situation like this. So we're going to have the piece of string tied through the hole in the middle and attached to the pivot. And then we're going to have the sets of masses either side of the pivot so that they're both acting to rotate it in opposite directions. And we'd need to make sure their moments were equal to each other. And the W1 you can see on there, as it says on the diagram, is the weight force from one set of masses. W2 is the weight force from the other set of masses. And the weight force times by their distance from the string should be equal to one another. So describe how two sets of readings are taking, explaining how equilibrium is achieved in each case. So first, we're given freedom to choose the masses. So I picked 200 and 400. You can pick whatever you like as long as it works. So I'm going to hang that on the left hand end at 0 centimeters. So it's 50 centimeters from the pivot. Then I'm going to put 400 grams on the right hand end and slide it towards the pivot until it balances, which should be around the 75 centimeter mark. So it's 25 centimeters from the pivot, or essentially half the distance. We could do another set, so let's do it another way around. Let's put 100 grams on the right hand end and then hang 300 grams on the left-hand end and slide it towards the pivot, which should be about 33.3 centimeters or 16.6 from the pivot. So that would give you two sets of data. And then in terms of actually recording that and showing that that is indeed in equilibrium, we've got the masses, the weight force, the distance from the pivot, and then the moments. And we can see in each of those two cases, the moments end up being equal and opposite because they're rotating it in opposite directions. And that finishes this moments video.